So we can start. Today we have the logical continuation of our previous topic. Previous topic was phonon dispersion, and now we are going to phonon density of states. So this is the same logic as we had for electronics properties. We had the band structure plot, and then we plotted density of states of band structure, but there are some differences because phonon dispersion is not band structure. We had so now we will have some theoretical introduction, then I will make calculations. For these calculations, I will show you next parallelization level. I think now after Yiji's workshop, you are ready for this sacral knowledge. And then we will calculate density of states for Titan gallium. Okay. I will shortly remind you what we have discussed last time, because last time was 3 weeks ago. We discussed phonons. So we discussed phonons, and I showed you the simplest model. In this model, we have a chain of these atoms, balls here, which are connected by springs. They are the same, these balls, and we now the distance between them, a, and then we shift all of them, and we mark new coordinates of these balls with un plus 1, un plus 2, and so on. And we have n. Big N is the total number of these balls. Then we can calculate the total energy, because all of them, they're just connected by Hooke's law. It's like J x squared x squared divided by 2, where x squared is difference between coordinates of neighbor items. So I can write the total energy of the system with n equal in n multiply on phi. It's energy between two these balls. Then I can apply some mathematic. In this case, it's a Taylor expansion. This is just and we see that here we have this Hooke's law, J on x squared, but the x will be sum of differences between neighbor atom coordinates squared. Then we use just Newton's equation, like m acceleration, second derivative of coordinate. This will be is by default. It's like some energy. It's like partial derivative of energy by coordinate. And inserting this harmonic energy to this equation, we'll get rather simple thing. We'll get that this m multiplied on acceleration will be just j. This is parameter for these springs, and just coordinates between this, and these atoms. We will shoot them. We can try to solve this equation. So this is differential equation, second order differential equation. We can substitute this u. This is the common way of solving this kind of differential equations. We substitute this u here, take all needful derivatives, and you get dispersion, omega dispersion. So this is what last time we have built it. So we have built it omega dependent on k. So it was frequency and wave vector. So omega divided by k. So this is phonon dispersion, frequency dispersion for this chain, for this super simple chain. If I will build this energy, I will see that we have some kind of brilliant zone. Here will be 0. Here will be edges of brilliant zones like p divided by a. And then we are going to more complicated case. When we have different kind of balls and different kind of springs between these balls, we are going by the same schema. here we will have energy of one spring, I mean this and this, with this equation. So here is difference between un here and un minus 1 un. So this is, and j, there are two different parameters for these springs. You have slightly more complicated equation. We'll have two formulas, two functions for un big, for un small, to substitute here and to get this system of equation, which is called secular equation, українською вікове рівняння. And this is for two types of phonons. This is analogous of this equation. Yeah. So if we will have this thing in one dimension, we will have this. But for two dimensions, we have this. And for n dimensions, we will have n. We will have some matrix with rank n. And we have to solve this system of n equations. We can solve it for two dimensional case. We'll get two bands. We'll have more complicated frequency dispersion, and we'll have two bands. One of the band we call acoustic band, which goes from the center of brilliant zone from 0 point, and it's like sound oscillations. So all these phonons, it's you see, it's harmonic oscillations of the atoms. And for acoustic mode, we can associate it with sound in this structure, in this crystal. And this is so-called optical bonds. Why optical? Because they play some important role for Raman spectra, for some other optical properties. Okay, how we can calculate it for not for two different atoms, but for crystal with n atoms, where n can go to infinite. We can go to Abinishek equations. Here we have this Schrödinger equation as for DFT, but when we studied it last term, I divided it into two parts. One part, so we have neglected by one part. It was like Oppenheimer approximation. So we divided it by just ions, which are very, very slowly and very big compared to electrons, and to electron part. And we then neglected ions part, but here we can't neglect ions part because the most important thing we have for phonons is this ions. So we had to solve the whole Schrödinger equation, and we had to solve this. So this is the secular equation, but for n-dimensional matrix. So we have this matrix which calls dynamical matrix, and we will solve this dynamical matrix through our calculations. Last time I also told you about this. So how we define the ions coordinate in some unit cell. So we have some 0 point of our coordinates. Then we move to so it's like coordinate of ion I. This is ion I in unit cell number H. So from our 0 unit cell, let's call it 0 unit cell, we should go on some amount of unit cells, and we will say that okay, on L unit cell you have this ion, and in this L unit cell this ion occupies S state, so it's like just coordinate of this ion in this unit cell L, and we distorted it in some way. So the idea is to distort. So it calls density perturbation theory, because we distort our crystals in very small distortion. They are very small. That's why we had to calculate it very precisely. So that's why we had to relax our structures to 10 in -8, for example, proximity for forces, because these distortions are very small, and if you have some huge forces acting on the ions, you will just not see nothing. So it's better for ions to be in equilibrium state. Then we can calculate the constants of interatomic forces. What are these constants? It's just second derivative from energy, but if we will compare it with our simple case, this is J. This is for one dimensional case, it's J. For two different atoms, is G, big G and small g. And here for n dimensionals, we have this matrix. So this is a constants of the interatomic forces between atoms. Between each atom, we have this constants. Then we this is in real space, but we make all calculations in reciprocal space. So we have to go to reciprocal space. And what is the way to create to move from real space to reciprocal space for some matrix? It's to apply Fourier transformation to it. So we applied Fourier transformation on this matrix. We got some other matrix. Then we got the new coordinate in this reciprocal space for this ion. It's almost like this, but we have this exponent term from which arose from Fourier transformation. And then we have this matrix in reciprocal space. This is what we solve in our ph.x stage in quantum espresso calculation. This is yeah, and okay, this is optical models. This is acoustic models. Yeah, so in acoustic models we go in one direction. In optical we go in the opposite directions. Yeah, and here you see the frequency is 0 because we are here in gamma point, and here we have rather huge frequency. And this is, I think this is Z. This is ZO, and this is two models which are degenerate because they have almost the same frequency. It means that they are in one point. Here, I also wanted to show you how the plot of Phonon dispersion changes when you use a Q mesh 222 or 333 or 444, but nobody sent me this salvation of this, but maybe I ask it for next time. So maybe I will show you it next time from one of your homeworks. How this plot changes when we choose different Q mesh of Q points. And now about the electronic density of states, few words. I want to again recommend you this book. It's like Materials, but it's electronic structure of materials by Adrian Sutton. I will compare them with phonon DOS and electronic DOS. So electronic DOS, we just know what happens. So we take some in reciprocal space. We take some sphere in brilliant zone. The sphere will be with some radius k. We have the volume of one state, and then we can calculate number of states in this volume. So we just divide this volume, the sphere's volume by one state volume, make some transformations, and get something like this. So we have number of states dependent from the energy, from energy differences, and then we can divide it by energy, and we have some function which shows number of states per some interval, some electronic interval. In our equations, we set it normally to 0.1 or 0.01 or something like this. We have this parameter, energy parameter in DOS. And then I recommend you this book, Introduction to Lattice Dynamics. We have a lot of things about phonons in all other kinds of crystals. It's really cool book. I think I sent it answer to you, or maybe I will send it today if I forgot to do it. We have the same thing. So we have some sphere, some volume of one state, but here we worked with energy, and here we will work with frequency. So this frequency has this kind of dispersion, like c multiplied by k. C is some velocity. It can be velocity of sound, for example. In relativistic case, it will be a velocity of light, but it will be phonon. It will be not some frequency for atoms, for ions. So we'll have very close equation. If I will remove this d omega, you have very close equation. So g omega, it will be it's some constant, and omega squared d omega. Here we have like some constant and square root from this from energy. Yeah, here I try to show you what to do next, how we can bound a frequency to energy. So it's just from Max Planck equation, like energy is h omega on this states, on this quantum states. Then we apply some temperature. We can apply temperature because all these frequencies, because phonon frequencies, they changes with temperature. It's very important temperature, because phonons are collective moves of atoms, and when we apply some temperature, these atoms began to move chaotically. That's why temperature is very important. We apply some Boltzmann equation, and then we can plot this number of states from this parameter, temperature and omega. Okay, maybe it's okay. Maybe it is not so important to do it step by step. So I just showed here how to get the energy, how we can integrate the number of states, this integral from 0 to omega to d by omega, d by frequency, and yeah, this is what I want to show you. What we'll get from these equations. So what we'll get from this equation? We'll get some very small doses at low frequencies. So at rather low frequencies, because you see it's like terahertz, 1 terahertz, 2 terahertz. So below 2 terahertz, frequency has quadratic law. So it moves like quadratic law, and we can play with it. So we can say that let's say our frequency is too low, and then we'll from this equation we'll get quadratic law. For bigger frequencies, our doses they are more complex. Yeah, and overall it will be like overall the logic of this phonon dose is the same as for electronic dose. So we should calculate each state in this plot, like here. By the way, why we have so low amount of doses till some frequency? Because here we have only 3 acoustic models, and they are at some angles. They are not so wide, and that's why they will create low amount of doses. It was the same thing as for electronic states when we have some not plane. So for example, this band will create a lot of doses. Yeah, but this band will create rather low amount of doses. That's why we always will have this tail. This tail will goes to 0. At 0, it should be zero number of doses because we have zero frequency. Okay, and now we can proceed to calculations. We will calculate the structure of titan gallium. It has only 2 atoms. That's why it's rather easy to calculate it. It will not take a lot of time. We will make the same. We will go by the same path as for previous seminar, and then we will make this additional thing for Phonon calculations, and we will calculate it for different K measures. So you have your files, and we can start, and then also I will show you on this on third step. I will show you how to add additional parallelization level to our calculation. We can start from relaxation. It's very easy, and we can. Yeah, the files are already filled because in other case we will spend all the time filling them. I hope now at the stage you are familiar with all these files, so it should be okay. I hope we can use 16 cores because in other case it will take a lot of time. Okay, we are going to relax. Yeah, you can try 16 cores. And we'll see if it works. So I will change here all these files for 8. I will increase that. Yeah, we can use 16. Then we can q sub qe script and see, and we'll see what happens. For me, it works. Yeah, looks like it works. It will take like maybe 2 minutes, something like this. 16. It is interesting if cluster has the cores for all of us for 16 cores. I hope it has. Maybe we can look at our script with new eyes after our workshop, which was great, I think. You see in the script, this is that PBS model, which Yizhe talked about. So just name, some output files, like for debugging, like QE log and so on. Then we use this parallelization thing, like ppn16. He also showed it. We can use more nodes, but now I don't see. I see that we don't need more nodes. So it's like 16 cores is okay. Wall time 59 because we want to stay in the short queue. This is our short queue. Yeah, and then maybe before all these comments was not so clear for you. This Yizhe also showed some kind of this comment. So it's like host. It means like for me it will be or Feia. So it's like the address of my folder. SSH. It just by default SSH. PBS or exadir. So it just passed to Quantum Espresso dir, where all these modules like ph.x, ph.x, and some other modules are stored. This is temporary dir. Maybe you remember how Yizhe talked about the Scratch dirs, that in some cases we should create some Scratch folders and make calculations there, but here it is commented because we don't need it. So it's another architecture for this cluster, so we don't need it. Then in file out file with the names, it's also obvious. And this thing, useful information for debugging. This information goes to our QE.log file. It's like echo running on host, and in this file we will see, for example, I can show you this file for some structure maybe, or maybe for still going. You see, this is our QE.log script running on host A47. Yeah, you already know how we connect to this host. Echo running on host, so it just display our information running on host A47. So if something will happen to this calculation, I know which host is capable of it. Then it's like time. Time is time. Time is Tuesday, April 9. It was yesterday. Yesterday I made this test calculations. U limit 64. It's a number of cores available on this A47 node. Echo PBS node file. It means where this file when you use PBS, so when you like Q sub minus E in interactive mode, it assigns you all free nodes in which you can go. And this file with these free nodes, it is stored in some file on the cluster, and this is passed to this cluster, and it shows the core from the node from this core. If you use, for example, two nodes, it will be like R47 and R48, something like this. Yeah, PBS node file cut. So this is cut. Yeah, what is cut? Cut, it means that we see the content of this file, and the content of this file is A47, just this, because we have only one assigned node. And then it's like information in this file, yeah, in this node file. It's like np8, it means number of nodes, export library, because we in each workshop we also exported this library for GCC 13, because without this library we can do nothing. Then what it makes, it goes to this this folder, relaxation folder. Then it starts our command mp run minus n, it means 8 nodes, host file, this host file, it means that it assigned to the node 47, and then just our Quantum Espresso command opt QE7.2 bin ph.x, it just this is QE PBS or exadir, yeah. Minus n pool 4, it means that we this parallelization for key points. Yeah, and then when the calculation stops, it sent us some message. The following foreign point exception, I signaling something like EEE, invalid flag, stop 3. So it means that we had to have 8, 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 stop commands for each of these 8 processors. Yeah, and then it shows like mp run detects that one or more processes excited with non-zero status. It means that our calculation was done. Yeah, so maybe this is what makes this echo part. Then how I create? So I can I have two options. One option is to write here the number of processors by hand, like 8 or 16 or something like this, or I can automatize it and I can use this like np parameter, number of processors, and I can take it from node file. In node file, I have also always the number of processors, like host 847 and number of processors. And it's like 8. Here it will be 8 for this calculation. So export library cd to pbs workdir. I showed you this export library path. Yeah, this is it. Export all these libraries, then cd to workdir. Yeah, here's my cd to workdir. This is. Then launch this script. This is this launch this command. Yeah, and then it's some information that we have finished our calculation. So I hope the script now looks for you very, very easy, because it's really not so hard. Okay, I hope our calculation was done. Done. Yeah, it's done. Now what should we do? We should take some information. We should take CLDM for our system. We should take CLDM in the, it will be in the end, yeah? This is our CLDM. New parameters, it was relaxed. And for which, yeah, you see, it was really good relaxed. For forces, we have zero forces acting on atoms. So those atoms, they're located in some perfect positions. That's why there are no forces acting on it. This is great for calculations. We have very, very small pressure on our unit cell. It means that our cell is not so ideal, but it is also okay, because 0.11 kilobars is okay. And I take, and we started from what we started? We started from we started from this point, minus 28. Of course, this is not acceptable for any Phonon calculations, because we will have huge error. Okay, we are going to SCF. Then I want to just insert this new CLDM here. Don't forget to do it. Don't forget to insert here new CLDM. If you want, I can tell a few words about the system. I hope that you already know it. I mean, this IBRAV 6 and so other thing. If somebody wants, I can take a look on the structure. Why not? Okay, I'll spend 5 minutes for it. Titan, yeah, you can start calculating, but it will take like less than a minute. You see, what thing is very important. This convergence threshold minus 12. It was minus 8 in all our previous calculations, and here it will be minus 12. Yesterday I forgot to change it. Yesterday I made calculation with minus 8, and it failed. So I couldn't calculate phonons, because accuracy was not enough for phonons. We had to have really huge accuracy. So yeah, we can start this calculation, but really it will take. Sub QE script. Okay, we can now return to this input file and spend few minutes start exploring materials. So from where I take it, titanium, and here is our system. I'm looking for the very, very simple structure, this structure. Maybe Yeah, I think this is the most simple. Because we don't want the hours of calculations. This is our Titan Valley. Tetra, I can't read this word. Tetra auricupride structure. Tetra auricupride. So auricupride, I think it's like aurum and cuprum, like gold. We have tetragonal structure, tetragonal. So in pw.x, we can go to eyebrow. Eyebrow, I'm looking for tetragonal. Eyebrow, we have this. Yeah, we have two options: tetragonal P, and it means primitive, or I. It always means base. It's like volume centered. It's I. So tetragonal P and I. What is our option? Our option is P, because you see symbol P4 MMM. P, it means that we have this primitive cell. Yeah, primitive Bravais lattice. 4, it means that we can rotate it on 19 grad. And MMM, it means that we can make mirror symmetry in all axes, X, Y, Z. So this is some kind of. So I choose 6 for our equations, 6. Then I take starting CLDM1 and CLDM3 because I had to take CLDM1 by default, and CLDM3 it's like C divided by A. I am going here. I take A like 2.8. I then move it to Bohr radius. And then I divide this C by A, and I take the second CLDM. Here are calculated CLDMs, yeah, of course. But number of atoms 2, number of types atoms 2. You cut WFC 80. I took just why I took 80 because it's okay for Raleigh. We can see like suggested minimum cutoff 43 for titanium. Titanium is like 52, and I think that 80 is okay for both of them. Yeah. What else? Smearing Gauss and the Gauss 001, and BND, number of bonds. And then this, and I think maybe there's titanium. The coordinates I can take from here. I can just see Pascal, and I take the coordinates titanium and gallium. That's not nothing nothing difficult. So I hope all these SCVF calculations was stopped. Yes. Now what should I do next? I had to move to Phonons folder. I have this Phonons folder, and I have to move this folder, TiGa save, and XML file. These two files, which will be used by Phonons to go to make a creation. So I just copy it. So you have to copy .save folder, and you have to copy XML file. Yeah. And XML, don't forget it because it will not work. Hmm? It needs charge density. So we usually we cannot to calculate to copy these WFC files. Sometimes here it's like they're not huge, so we can copy it. If you will, you worked with Apatit, yeah? For Apatit, how much it was? Like 7 gigabytes. 70. 17 gigabytes from my experience is like was like 100 gigabytes of this file. So you can you shouldn't copy all these WFC files. We copy them just by proximity, because we just make one copy move, and you need this file. So pseudopotentials, you need charge density, because it's the file where all charge density is stored. Mikhailo had already make some pictures for charge density for different system, for intercalated graphene system, and that information was stored somewhere here. And data file schema is like our input file, and PO is also important file. So this is files what we really need. But usually we copy all the same folder, because it's really not huge. Yeah. And now I want to show you something interesting in our script. Feia script. You see, I hope all of you have 16 cores for the script, yeah. And we can go there, and you see, I changed slightly this command line. It was in previous creations. It was npool for. How do you understand this npool for command? We use it from time to time, but it means that we calculate it means that we calculate 4 points simultaneously. So if we have 16 nodes, 16 cores, so we divided by 4, it means that each key point will be created by 4. So it slightly makes our calculation pass. And
let's say 32 key points. The whole number will be split in 4 parallel processes.
Yeah.
So one for one bunch of cores calculates 8 key points, and the other one another 8 key points, and so on.
Yes. I can show. I can illustrate it from one of our previous labs. I hope it should be somewhere here. Bends out. Oh, the symmetry. Okay, that's not what I wanted. I wanted yes, this bends out. I will illustrate it for you. You see, we have it's for some of our previous calculations. We have 211 key points, and if I will not specify this, npool, I will have like all my cores will calculate each key point. So I will have 211 calculations. But I think I specified 2, and I think it was like some kind of npool 2 here, because you see one of 160 in this npool. Parameter pool, it's like it's just term from this parallelization stuff. It likes you take these key points into one pool, and it considered as one entity. So 211 I divide by 2, it's like 106, and one pool will be from only one key point, not from 2, but from only one, because it don't divide exactly by 2 to 211. And you see, computing KPT one of the in this pool. So it means that all our cores, they created 2 key points simultaneously. This is what key point. This is what npool makes. And now we have another parameter which calls an image. Okay, we can start, and I will tell you a few more words about this image, Q sub QE. We use it. We copied dot save structure dot save. So we use it. So I started it. I hope it will, for all of you, it will work. It will run for 16 cores. You should check it. If it's in the queue, you had to go to maybe long queue, not from short queue. Okay, and it was parameter and image 2. It means that simultaneously we will calculate 2 images. Yeah, what is image? Q points. So it was like n pool is for K points, and this is for Q points. I will remind you what okay, you see, I will show you our previous calculation. To the right, lab 14 silicon, and to the left, lab 15 titan gallium. Yeah, and you see here it was like ph0, the folder, and in this ph0 it was all information about the calculation for each nodes, and here we have ph0 and ph1. It means that we have took all the Q points and divided them by 2 bunches. So 8 cores calculate 1 bunch of Q points, and 8 another cores calculate another bunch of cores. Because we have 16 cores, yeah, we divided by 2. It means that each Q point will be created by 8 cores. Yeah. Yeah, and in that Q points, in each of the calculations, yeah, they will be divided by 4 because for Q points. And now, what is also interesting here? You see, I have out TiGa ph out. What will be here? What it tells me? It tells me the processes distributed on one node pass image division, and image equals 2. Then it has some, yeah, here's npool. Npool also, K-point division also works. Yeah, npool equals 4. And then we have these 6 Q points. So we just apply this vector. What is Q point? So this is, yeah, it's some perturbations. So it means that we have this G vector. Yeah, this is G vector. It shows our some direction in crystal structure, and then we distort atoms in this direction. So, and we can make the distortions by dividing this vector into some parts. It means these Q points. This nq1, 2, 2. It means that have 2, 2, and 2. Here it will be 0, 1, and 2. 0, 1, and 2. And we have all these combinations, and along all, and they will show you different directions in our cell propagation. So in the distortion propagation. So distortion propagates in some direction, and this Q point shows us the direction of propagation of the distortion. All this UN, UN minus 2, and so on. Yeah. Yeah, of course. We take the symmetry, then we divide it in some directions. Yeah, and along the directions we make these distortions of atoms. So we move ions in some very, very small distortions. And 2 by 2 by 2, it's 8. Yeah, if we have no symmetry, we will have 8 Q points. So we will have 8 directions of these distortions in our atom. But here we have some symmetry. That's why we have not 8, we have 6 Q points for this structure. Yeah, for the structure we have this here they are 0, 0, 0, of course, 0, 0 minus 35 something, then minus 5, 0, minus 5. It's all in Brilliant zone. It's like key points. It serves the logic for key points, but key points is
for integrating of Brilliant zone energy, and this is for creating these distortions. And now, as I think our calculation divided, so it will calculate 3 first Q points on 8 cores, and 3 from 4 to 6, it will calculate on another 8 key points. And how we can get it? That you see, this is, I opened like ph out file. I have here the 6 Q points here, and then it shows I am image number 0. Yeah, it's super creepy, but okay. Image polarization. There are 2 images and 28 representations. What is representation? So in each of these Q points, we have 6 models. Yeah, because we have 2 atoms, we have 2 dimensions of freedom. That's why we have 3. So it's like 3 multiplied by 2, 6, 3 acoustic models and 3 optical models. Here, these models: one model, 2 and 2, so 6 together. And they apply, the program applies some symmetry on these models and sorting them. So it says that this first model, I think is some kind of acoustic model, we can combine it by symmetry with all other models, so it will stand alone. This also will stand alone. Here, 2 and 2, they combine it. And all of this model stuff we call representations. So one model, representation 1, one model, representation 2, 2 models, representation 3, 2 models, representation 4. So for this Q points, we have 4 representations. Each of these representations, it stands alone as self-calculation. So here is like representation 1, model 1. It means that we have crystal with some distortions. So each representation shows some crystal. This is our titanium gallium crystal with some distortion in some direction in model 1. So model 1 is some kind of acoustic model. So in direction of this acoustic model, we have some distortions. And it calculates this crystal. And here we see the common self-consistent calculation. So each representation, each self-consistent calculation. We are going with super huge accuracy, like -13. Why -13? Because I have pointed in my file. Where is it? Here, yeah. You see, I typed -12. This is my accuracy, which was in SF calculation, in SF step. We had accuracy -12. Here we also have accuracy -12. It's better maybe -14, but okay. And here is -13 because it's something which is better. It looks for something which is better than -12. So previous was -11, now it's -13, and it thinks that we can stop. At least we achieved that accuracy. So we have made this SF calculation for this model, for some acoustic, let's say, model, in 6 steps, in 6 SF steps, and end of self-consistent calculations. So it's success. Then we are going to another representation, another self-consistent calculation. And here in these calculations, we will have this n-pool key points. So each of them, they so for each of these calculations, we had to we have k points, yeah, and we divide them by that number in n-pool. I hope this was understandable, the logic, how it works. And we have divided, so for 8 atoms, for 8 cores, we have divided, we have this 3 Q points, and for others 8 cores, we have another 3 Q points. Okay, and what is so? So this is this creepy message. Image parallelization. So there are 2 images and 28 representations. So 2 images. 28 representations means that we will have 28 SF calculations for each of them. first Q point has only 4 representation. Yeah, and then the estimated total work is 56 self-consistent runs. That's why phonons are so huge, because it's 56 self-consistent runs.
12 iterations in each of those 56.
It's like 6 or 7 or more iterations in each. Yeah, it's really huge. I am image number 0. It's like first. Yeah, and my work is about 28 SCF runs. So on 8 atoms, on 8 processes, we'll have 28 SCF runs. I calculate Q point number 1 representation 0, 1, 2. 0 is like some basic representation. 1, 2, 3, 4. Yeah. For first Q point, we have this 4 representations. Second key point, where is it? Yeah, second key point representations 1, 4, and third key point represents 1, 6. And we see for first and second we have only 4 representations, because they are they have some symmetry, this and this. But this point, it don't have symmetry. That's why we will use all 6 points. But our crystal has symmetry. That's why we have only 6 representations, 6 key points, but not 8 key points. So some of them will contain 2 or maybe 3 key points. I don't know. We can check. And now we had to wait. And also, you see, this is pH out. And we have out 0, 1. This is another out. This is out for another bunch of images. It will be the same as first out. You see, it also says blah, blah. But here it says, I am image number 1. It was 0. And my work is about 28 SCF runs. I calculate Q point number 4. So this will calculate. Number 5, this. And number 6, this. And point number 4 is rather creepy because it don't have symmetry. This 5 and 6 have symmetry, though we don't need to create all 6 key points, but so we don't create all 6 modes in each representation. We can create only 4 modes. Yeah. Some of them was generated by symmetry. Yeah, and it starts the calculation. So it's like you can divide 114 on 14. It will be what it will be like 8. Yeah. Yeah, it should be like 8. It means that 8 cores works on these things. And this is another output. So we have 2 out. If we, for example, if we type number of images like 4, yeah, we will have 4 bunches of these representations, and each will be created on 4 cores. I don't know if this is a good idea. So at some place, so at some number of images, it will not make sense. So maybe 4 on 4 cores, it is not so good as to. I don't know. We can explore it, for example. See. So it finished 1 representation. It is now it's on the second stage. Representation 3, models 3 and 4. Maybe you didn't refresh it. If you will refresh this file. You have tail, yeah? But maybe it's representation of this second key point. It can be representation of first, but of second key point. For example, yeah, you see, it started the third key point. Yeah. So I think we have to wait like a few more minutes and it will finish the calculation. Mm-hmm.
Imagine we just have a pulse, right? And if we have say 24 cores, you might divide it into 4, 6, or 8 pools. Is it like intuitively understandable? Which is better, or should be tested for each?
I don't know. I think we can, if I think we should test it. So it means, for example, if we will have 4 points on 4 cores, or maybe we should to calculate 2 points on 2 cores. So which will be better? Yeah. So
Yeah, it's yeah, so the only way find out to this.
we can also make like
It just carries the set, and it's a common saying that's like the test profile, like everything.
yeah. I think usually we should test it. For example, you can you have 16 cores and you can type 16. Yeah, it means that it will calculate each key point on each core. But I don't think that this is very useful.
In this case, the parallelization routine itself starts to overwhelm.
Yeah. So it's we have a lot of things are described in here. So Quantum Espresso, it's from its guide, parallelization levels. Yeah, we have world is a group of all processors. It's like we have all the processors. Images. So images, it is very high level of parallelization because we let's say we can take 28 SF cycles and go them on some number of cores. Pools. Each image can be split into pools, each taking a group of key points. This is another. We can also parallelize bands. We can say like, so because each SF cycle, it has this number of bands. For example, 20. Yeah, I stated 20. I can type, for example, 4. It means that it will. So we have 16 cores. We divided them on 2 because number of images is 2. It means that for each SF cycles inside this Phonon calculation, we will apply 8 cores. Yeah, 8 cores for SF cycle. Then we divide this 8 cores on 4 because we have our number of pools 4 number of cores. So it means that we will use 2 processors to calculate each key point in this thing. Yeah, and then you can these 2 cores you can also divide it. You can write, for example, write bands equals 2. It means that these 2 cores will be divided by 2. It means that one bench of bands will be created in one core and another bench of another core. And this is it. So we can't parallelize anymore. Yeah, because cores are finished. But if we will have, for example, you see this example, 4096 cores. Yeah, it has, it's like some kind on NEB, natural elastic band calculations, it's some other stuff. It's for calculating transition pathways. They use 8 images. It means that each of this image will be distributed across 512 processors. Then we choose number of pools, key points, 2. Key points distributed across 2 poles of 256 processors. It means this. Then we divide it by 4. It means we 3D FT, Fourier transformation. So we can also divide Fourier transformations. It's performed using 4 task groups. It's 64 processors at each. And the diagonalization of the subspace Hamiltonian is distributed to a square grid of 12 processors. So they divided by 4. Yeah. It's like when you have 469. I think on this cluster on the side it mentions like it has like 800 cores at all. Job done. Yeah, I hope that my job also done. Yeah, my job also done. It took 19 minutes. So what about you?
Mine
You're still running? Okay, 19 minutes, yeah. And I can see out 0, 1, another out for another bunch of. It should also be finished. Yeah, you see, it also finished, but there is no information that job done because our main processor was like ph out. So in ph out, job done. Okay, we can wait for all of you, but I think it was, yeah, it was successfully finished. Yeah, I think that on different nodes, maybe I see that in short, but I see that all processors in short QA have already stopped. Guys, Alexey, Mikhailo, you should check. Alexey?
I think the queue did something with us because my calculation is 17 minutes 40 seconds CPU time and 20 minutes
20 minutes.
So
Maybe it took the 3 minutes, 3 additional minutes to manage these 2 benches of this is I think this is the thing which Egypt described, that you had this parallel part, so it cores for each image, and then some time to manage all these 2 calculations, I don't know the exact.
probably just something with figure.
Okay, so we have calculated it. It's then we should go to the next point. It means that we had Q to R. This is model Q to R. In this model, I'll just remind you, we calculate interatomic force constant. So we calculate them and move them from reciprocal space to real space. Q to R to real, reciprocal to real. And it makes this module I don't want to change this QS script. Let's create another QS script. CP QS script PP post processing. Because I want you to have this image, the script with these images, and this is for post processing. So I will open this QS script post processing. Here, maybe I can change the name like PP. Then here I should change. What should I also change? Executable Q to R dot X. This is our model, and here it will be like also Q to R. Q to R. Yeah. And it also don't work with these images and pull stuff. So I had to delete it. That's why I copied it, because I want to save for you this file with images. But here I had to delete this thing. I mean, and pull and in image. Yeah. Because it just sync for ph. It don't just Q to R. It's very simple sync. That's why we don't need it. Also, we don't need parallelization at all, but it works. So in previous versions of Quantum Espresso, it didn't work, but now it works. So I don't care because of it. I think it's super fast. It's really super fast in one core. So I think nobody cares about it. And let's see what will happen. it will take really like seconds. If everything is okay, I hope everything is okay. Yeah, everything is okay. So for me, it's like it's Q2R out. So everything is okay. What it makes it says reading force constant from file, reading force constant from file. Then FFT, it means as Fourier transformation check success, sum of imaginary terms 10 minus 12. Okay, everything's okay. Now we can proceed to another step, and we should calculate this dynamic matrix about which I told you in the beginning of our lecture. So we should this alpha frequency. Now we are going to next step. So we had successfully calculated this interatomic force constant. We have some matrix, and now we should calculate the data for our plot. So it's like this is file which will contain force constants. So this Q2R creates file, this file K222 FC. It means force constants. And then we take this force constants and diagonalize dynamic matrix with this force constant and create from this file frequency with it should looks like this. Yeah, and here I also type our path. It is the same as we used in band structure creations. So I just use the path in Brilliant Zone to see how this phonon dispersion will be changed in the Brilliant Zone. And it makes, I can change the script pp. This is our pp. And I want to change executable to matdyn.x. Matdyn, dynamical matrix. Matdyn. And from this calculation, we will get, yeah, matdyn. Then I launch it. Sub QE open. It will also take like 1 second or less than second. Yeah, it was like 0.2 seconds, 0.02 seconds. So it's not like even not like 1 second, it was 50 times less. Yeah, it created. By the way, we have a lot of files. TiGa din0. It means dynamical matrices for our Q points, like first Q point, the dynamical matrix, and these frequencies, and for each of them. And we have this frequency file, where it is, freq. Yeah, we have in very, very inconvenient way, inconvenient form. This is frequency in gigahertz, and this is some like, this is key point, Q point, yeah. And this is frequencies, like there should be 6 of them. First 3 acoustic and then optical. Yeah, and now we can calculate, we can make the plot, we can plot them. What you showed, it's better to use this tip to sub minus E, like on our workshop. So go to interactive mode, yeah, on A47. Which nodes do you have? Also A47, yeah. we can make this our Phonon Python script here. Lab 15 phonons. So a lot of files. Yeah, I will open this fast. Okay, we have Python script TiGa phonons.py. Yeah, TiGa phonons.py. Yeah, and it is rather simple. Pass to this file. We will plot this file frequency GP in convenient form. Some limits, like in Y, we will have frequency. So it's like, so I type at 350 gigahertz, and this is just our key, just our Brilliant zone. So it's like key vector. Points. These points are attributed to this path. How you can create these points? You can create it by your hands, or like Pythagoras theorem in 3D, like squared, like this minus this squared plus this minus this squared plus this minus this squared, and square root from this. And then the same for each. Or you can provide band structure calculations, and in bands to out, you will see all those points. So they are the same. They are the same as we take, for example, for calculating electronic bands. Okay. It was my presentation. Yeah, phonons. And then it's like read phonon data. I just read it from the file. Plot phonon dispersion. Here are these labels, X points, X labels, like X, M, gamma, Z. And plot it. And we will have this file, ph.x. Python 6, TiGa, phonons py. Where is my file? My file is yeah, here it is. ph.x. Yeah, that's our phonon dispersion. Of course, this 2 Q points is not enough. We had to take at least 3, 3, 3, or maybe 4, 4, 4. But it will take more than 20 minutes. Okay, our 3 acoustic modes, yeah. In this direction, gamma Z, I think that gamma Z direction is like vertical direction. 2 of them degenerate, transversable. This is always longitudinal. So this the lowest is always longitudinal mode, and this transversable. So they degenerated. We have this 1, 2, and 3 optical branches. Here they are. Okay, now we can calculate phonon dose. We should exit this node. Yeah, exit, because it will not work on the node. And I want to launch this file. It's also like matdyn, like this, but with different options. So here we calculated phonon dispersion in band form. Yeah, you see Q in band form, like band structure. here we will create DOS, and I had to just type this command DOS true, and here will be like nk1. It means that we take a number of key points to calculate this density of states, and the more key points we have, the better. Yeah, but okay, if you will take like 100, 100, 100, the difference will be negligible from, for example, 30, 30, 30. But between 10 and 30, it will be difference, and we will explore it today, this difference. So this file, we had to change our pp script again. This file calls matdyn.x because I called it matdyn.x here and here. This is the only changes we need. matdyn.x. So this is input, yeah. And I want to write the doses in file TiGa 10, 10, 10, because then we will change it. We had to distinguish them. QE. No, QE script pp. Yeah.
You are on.
Yeah, I'm on the node. It will take like parts of the seconds. Let's check if everything okay. matdyn.x out. Yeah, everything is okay. And we have this file. This file contains all our doses. And here it's very simple. Here we have frequency. Yeah, the frequency. Here we have total dose, and here we have partial dose for each atoms. This is for titanium, this is for gallium. And it's super easy, and I want to build it with TiGa ph DOS with this script. TiGa ph DOS. So I also go into the node q sub minus e. Go to this folder. Yeah, here I open in this script, I open this file 10, 10, 10. I set the limits. Here I made this function. You see, I made this parameter file path and n. N1 means that we can create total dose. It just means that we read first column, then second column, then third column. N1 total dose, N2 first atom, N3 second atom, and so on. And then I just plot it. So like 1 total dose, titan gallium, 2 we will T, 3 we will gallium. In all other forms, it's almost like our DOS script. Python 3.6 ph DOS. Yeah, I hope it works. We have this new file. And here it is. Yeah, you see. We have Phonon DOS, and we expected this behavior. You see, here we have very small amount of doses. Maybe we can do it here. I can do it like this. Here you see it's like quadratic. It's like quadratic dispersion, but with very low speed here. So it's very low. It's like what I expected from the theory. I had to have this very low start and then something random, but of course not random. Yeah, and we see that gallium makes a lot of frequencies on this, like 150 hertz. It's a mistake. It's not terahertz, it's gigahertz. Of course. So it's like 1 point, so on some optical branches, it will make a lot of doses, a lot of contributions. Then going further, we will have increasing titanium value. And what I propose to do now, I propose to okay, we can exit. Yeah, I want to change this file matdyn TiGa.matdyn.in. I want to change it. matdyn.in. I want to type here 2020, and want to see what will happen. So I increase the number of key points in 8 times, and I will change the name of the file to like 20. This is all the differences. Yeah. I can start the calculation. Here script pp. It will you see it takes more time. It was like 1.7 seconds, and we'll check how how for you it's still instant. For me, it's you have error. If you got the normal, maybe it. I will check it now. matdyn DOS out, yeah. I will check it now. Do you have this file TiGa 2020? It's also so something works wrong. For me, it's 16. It was 1.7, and now it took 17, and now it took 16. So maybe you had to wait. matdyn DOS out. Open it. Try to open it. I want to change it for 30. 30 and the file. So 30. Yeah, this is the changes I had to make. And I also launch it. So for 10, it was 1.7 seconds. For second, it was like 17 seconds. It was 10 times more. And now you guess your stakes. What will 14?
40.
40.
It's 10 times more once again.
Like 5 minutes, yeah? But it's cubic, yeah, it's cubic. So it's like
it probably was 8 times more.
30 is like 1.5 in the power of 3. 2 and like sometimes like
3.5.
3.5. So it's 17 and 30, like 60 seconds. My guess is 60 seconds. You should check. Yes, it still works. Yeah, it finished. I want to check this file. matdyn.x. Yeah, I was close. I thought that it was like 60 seconds. It took 68 seconds is the calculation. Okay, we have 3 files. So we have this TiGa 10, 10, 10, 20, 20, 20, 30, 30, 30. I want to compare them. I don't want to rewrite the script. I can copy our TiGa ph DOS file to some file like TiGa ph DOS comparison, for example. And I will change this comparison file, TiGa ph DOS comparison. So what should I do? I should specify the file path. Now I have 3 files. That's why it means that I should copy it. Ta-da! And it will be like DOS file path 2 for TiGa 20, 20, 20, and DOS file path 3. It will for TiGa 30, 30, 30, because I want to compare 3 files. Yeah. Then I had to change something here. So it's like, for example, here I will write it's like 10, 10, 10. Here it will be TiGa path, DOS file path 2. There should be 1. TiGa 20, 20, 20. And the same thing 3, 1, 30, 30, 30. So you should check if everything is okay. So DOS file path should be 1, 2, 3, and this additional parameter should be 1, 1, 1, because I want to create total DOS. And the names is appropriate file names. Yeah. And we can make maybe we also should change the file name as comparison. I'm going to the node q sub minus e. Then I go again to this folder lab 15 phonons, and I launch the script Python 6 ph DOS comparison. Let's see. Yeah, maybe something wrong. Yeah. For me, everything is perfect. Maybe you have some error somewhere. Yeah, okay. You can look at my and then you can try to build your own. You see, for you created, yeah. Mikhailo, Igor, Fedor. I hope you follow us. It means convergence of density of states. So we took 10, 10, 10. the worse accuracy. It is blue. Then we took orange, is accuracy slightly better, and green is the best accuracy, 30, 30, 30. And we see the differences. You see that differences, yeah, they are. So, for example, here it became more more smooth here. Somewhere the spikes go away. For example, this blue spike for 10, 10, 10, it moves to this spike. So because it was not so accurate, and that's why it was interpolated in some way and created this DOS. Yeah, and 30, 30, 30. And when, but you see, but the overall difference is not so huge. They are not the difference are not so critical. So if you will see this or this or this plot alone, you will not say that, oh, this is too bad, this is a really bad plot. If I will increase it like 40, 100 million, I will see the lower and the lower differences. So between 10 and 20, we see rather huge difference, and then between orange and green, we have really low, it's like cosmetic differences. So I think for between 40 and 30, it will be almost nothing difference. So this how we can converge this DOS. It means if you will make some paper and you can say that we checked these differences and we make this convergence test, and we see that, for example, 30 is the best. That's why we present it in our paper. And the last part, I think you guess it. We can plot it together, dispersion and this file calls phonons plus DOS, and I can try it. All these files, they are analogous to the same files for electronic, for bands, for electronic DOS. We have this file ph.x. Here it is. So what we expected. When we have flat bands like here, we have huge peaks. Yeah. When we have not flat bands like this, we have almost nothing in the DOS.
Why is the peak around 100?
Around 100, you mean this, yeah? Ah, this peak. Yeah, maybe this. Yeah, usually we had to see somewhere here. Yeah, some peak. Yeah, but we see some peak here. Yeah.
Yeah, crossing over the model.
No, they don't cross. They don't cross. It's if you will see that this they touch. So this band, it's like goes here and then here, and this band goes here. So you see that they're touching. Yeah, and this three bonds is like some kind of sound like bonds. So you can take the equation from sound, and you can compare it for sound as a crystal. Compare this with these bonds. So their physical meaning, and this is so the atoms, they are they vibrate in one direction. Yeah, optical in different directions, and optical it means like, so when you calculate Raman spectra, when you calculate some when you calculate some optical constants, you will somehow interact with these optical branches, because Raman spectra, for example, it's so they derivates from phonons. It's some oscillation of the atoms. Mikhail, I thought that you had some question.
I've had an idea why we see this peak.
Yeah.
Because we actually we calculate like the how do you call it, like K resolve K resolve plot only for
not for all paths. Yeah. I think that's the reason. Yeah.
So maybe there is some flat band.
Yeah. I think so. So yeah, I think that's the answer. We didn't take the whole brilliant zone path. It's resolution of the spot. So it means that we have I can maybe show you the formula. So it's how we dealing with this equation. So it's a resolution. So we can calculate it by dividing brilliant zone by 10. So it's like key points in brilliant zone in which we calculate this Phonon dose. So we can divide it by 10, and we'll have some points, and we then should interpolate between these points, or we can or we can take more points and then interpolate lower amount of space between them, and that's why it will be better. So you see that the bigger the better, but from some time the difference become negligible. For example, between even 20 and 30, difference is really very small. Yeah, but 10 and 20 we see some places where the difference can be huge. So if you don't have any questions, we can finish by today. Yeah. So thank you for joining the seminar. See you next time.